Consider that the first 2 points, I will explain a bit about the state of the art of satellite remote sensing. And then we move on with a technique we invented to try to understand how things work and how we manage to obtain underground scans. And then I will present some case studies. So a brief mention of the Pyramid of Cheops or Khnum Khufu. And then other things such as other experiments we conducted on the Gran Sasso in Italy, or on the Mosul Dam,
or on the Gotthard Tunnel before handing over to the professor.
So we employed the so-called synthetic aperture radars, and therefore I will explain to everyone what the word aperture itself means and what synthetic aperture is, because things need to be well understood. Well, it should be noted that synthetic aperture radars are mainly mounted on satellites that are in space. And predominantly, actually solely, not predominantly, they are placed in low orbit only. Low orbit is that orbit which occupy circles in space that have a distance from the Earth's surface ranging from 400 to 700 kilometers, so they are primarily close to us. Just to be clear, there are two other orbits, two fundamental orbits, the intermediate orbit are predominantly placed before and after the Van Allen belts, so around 14,000 kilometers and 18,000 kilometers. Why is it not advantageous to keep satellites in the Van Allen belts? Because they last less, and therefore you have to place them either before or after. Otherwise, things don't work. And who and what kind of satellites are they? They are GPS Global Positioning System satellites, or Galileo, the system for satellite positioning that we all use, for instance, to operate our satellite navigators from Galileo, which is the satellite, the European satellite system, and other GLONASS. And there are many others. In short, each an important block of the planet, yes, builds its own satellite positioning system. Then finally we have the farthest orbit, which is that of 36,000 kilometers. So we are well beyond the Van Allen belt, where usually one orbit of the satellite coincides with one rotation of the Earth. So to an observer on Earth, the satellite appears stationary, but it is not stationary because it rotates. Which then, in reality, we will see that it also forms other shapes, similar to figure eights. So it is not difficult. It is very difficult to keep the geostationary satellite still, which then there is an international organization called the International Telecommunication Union, the so-called ITU, which assigns to the countries of the world the so-called box where the satellite must be placed for telecommunications. So we have telecommunications, telepositioning, and then in the end, the closest orbit is remote sensing. But it's not exactly, because lately the low orbit is, from my point of view, the most massively used orbit, because recently other satellites are also being placed there, namely those for telecommunications and also in low orbit and the internet service. So we can say that the low orbit is very important. It is an orbit that it is very important because there is a distance from Earth that is very close. It goes... All right, so now let's see why it's called Synthetic Aperture Radar. Well, first of all, as the word itself suggests, radar is radio detection and ranging. It's a device used for detecting the objects that are far from it and then simultaneously measures their distance and over the years. So we say that this equipment was thought to be realizable at the beginning of the century because it was thought, well, then we can use electromagnetic waves to understand if there is something in front of us.
For example, pillangpitäessä, pohtaessa kenttä, it was certainly needed by navigators, and after the sinking of the Titanic, it was essential for ships to have radar on board.
Because it is important when sailing in the fog or sailing when the weather is bad to have the radar on to understand what is in front of us. The problem is that it took a lot of time and many years to develop it because in this case, let's call it the received power of the radar signal falls off with the fourth power of the distance. And this is a problem. It means that if I transmit, for example, 10, what I receive is 0.001 in terms of power, so a problem. So it took a long time. Some gentlemen had to invent special valves called, or TVT, called magnetron, which had the specific function of generate coherent radio frequency energy, and then this energy also needed to be high power. Okay, as the years went by, the idea was to try to install radar on board satellites. To do what? To consider generating electromagnetic images. So one was faced with a fundamental concept, a concept of physics, of classical physics itself, which was, in the past years, it was encountered, for example, with telescopes to visualize targets, the targets that are far away. It was necessary to act on a parameter, fundamental. This parameter is spatial resolution. This concept, and I'll also give you a scientific definition of spatial resolution. The spatial resolution is a distance, and it is a minimum distance, so that two objects can be distinguished separately. That is, if I have two objects,
these two objects,
if I make these two objects travel in the distance, and let's keep in mind this concept of distance because we will find it later in synthetic aperture radar at a certain point, and we observe them with anything, with a camera, with a photo camera, with anything. At a certain point, we will no longer recognize these two targets as separate because the distance is too great.
and so
Installing a radar at 600 kilometers altitude, you had to pay attention to the resolution. Physics tells us that the spatial resolution, the slide says lambda, the spatial resolution measured in meters is equal to, it is delta, which is equal to lambda times r divided by twice the aperture. Lambda is the wavelength of the parameter of the physical manifestation that I use for remote sensing. I can use anything. Electromagnetic waves, so the entire category of light up to gamma rays. Electromagnetic waves, acoustic waves, hence matter. Matter also has a wavelength. De Broglie told us that in the times of quantum mechanics. Or indeed I can use, for example, electrons.
in the Iron Eye.
For example, when we have to use the electron microscope, electronic stands for electrons. So divided by 2, you see that lambda and r are in the numerator. This means that the more I increase r, the larger delta becomes. However, I need delta to be small because there is a minimum distance to ensure that two objects can be distinguished separately. Divided by the aperture twice. I have the... It's all about that, all about that. The aperture. If I have a camera, to see the details well, I need to have a camera with a large aperture.
Why do I have to?
I need to have a broad vision of this thing, wide aperture. Try, for example, to take a photo with a camera without a lens. It can be done, but what I get, it's something that is not the photo. I obtain something, but it's not the photo. I absolutely have to insert the lens, because the lens allows me to see things the way we are used to seeing them. That is after a Fourier transform process. What is the Fourier transform? The Fourier transform is that mathematical operator that professor, excuse my term, it transforms everything that is a wave into particle, because we are used to seeing things compressed. We see this pen because we've done a Fourier transform operation. Our eyes are moment by moment calculating a Fourier transform. So, to mount a radar in space, it was necessary to design the system with a large aperture. If you do the calculations for this aperture, then using the inverse formula, suppose, for example, we set a spatial resolution equal to 1 meter, you see that the aperture I must have in space must be very large. Kilometers, 20 kilometers, 30 kilometers. This means that it was necessary to install in space an antenna 20 or 30 kilometers long. An impossible thing. It's not possible to carry out, that is, assemble a piece of iron 20 kilometers long on a space vector to then position it in orbit in space. Well, at a certain point, there was a period, for example, in the 1950s, when this project was set aside due to its unreal unfeasibility. It's not possible.
And how do you do it?
And it is done like this. There was a person called Carl Wiley, a scientist who worked
For Bell. In the United States.
whom I define as a heretic. There is always the clash between orthodox thinking and heretical thinking. If you look back in time and analyze what happened over time, when we all analyze it, we discover that heretical thought always wins. It always wins. So heretical means arrow, arrow, air, freedom. What did Carl basically say? He said that it made no sense to install a 20 or 30 kilometer antenna in space. It was stupid, it was useless. He said, cut a piece of this antenna, for example 6 meters. You cut it with the grinder, take the grinder and really cut it. Then take this piece, this fragment of iron, you package it, put it in the vector, and throw it into space. then the orbit will take care of synthesizing what we want, even 80 kilometers of antenna. We will see that we have used, and here I take the opportunity to thank the two American providers who provided for free, not only to us, but to everyone, to the entire scientific community, to all people. They provided us with satellite data freely, with an aperture of 80 kilometers. An 80-kilometer aperture means a spatial resolution on the ground of about 6 or 7 centimeters. Very good. A very good resolution. Okay. So you see the orbit, or in this case the airplane, takes care of it, but it doesn't matter. One can imagine a satellite flying in space. And here I tell you that the satellites for remote sensing usually travel in a circular orbit, South Pole to North Pole, South Pole to North Pole. And then the Earth rotates beneath them. Below, the ecliptic remains constant due to geodetic physics. South Pole, North Pole, and therefore the Earth rotates under them. The satellites are able to take a picture of any point on Earth at least once a day. At least once a day. So they are very, from a scientific point of view, they are very appealing. Having overcome the problem of the opening, in this case, we perform time division scans in the same way. It is synthesized, synthesized virtually, but really an aperture, as long as we want, even 80 or 100 kilometers, doesn't matter, because what interests us is having the maximum resolution on the ground. Okay, so what does the satellite do? The satellite, I will try not to go on too long because I imagine it would be tedious, but I will try to explain it simply so we can all understand how it works. And practically, what does the satellite do? At the moment it performs the scan, let's call it in the direction of the orbit, and we call this orbit direction azimuth. What does it do? It transmits electromagnetic pulses to the ground and receives the echoes. Receiving these echoes, they are digitized and stored in the onboard memory. Then, when the satellite reaches, for example, a downlink point, throws the data to the ground, and the data is then distributed to people. Usually, these data are not usable directly, but they need to be processed to obtain an image. For example, look, see this little machine here. Look, as the satellite traverses its orbit, you see the waves it transmits being compressed on one side and expanded on the other. Now this effect is called the Doppler effect. And just to understand for everyone that the azimuthal part of the image is synthesized with sounds. Because by chance the Doppler band falls exactly within the acoustic band. So with Professor Malanga, acoustics, we focus our efforts on this acoustic word. Why acoustic? Because we were interested in looking under the pyramids. And we all have to understand that the electromagnetic interaction with matter is only superficial. Miracles cannot be performed. Yes, I could be able to transmit 1 gigawatt of photonic energy and maybe achieve 20 or 30 meters of penetration, but forced into the material. Yes, but who would give you 10 gigawatts? It's impossible. So we thought of exploiting and
acoustic energy to harness the phonon. Why? Because sound,
the physical manifestation of sound, which is nothing other than the vibration of matter, propagates very well indeed in matter, and the denser this matter is, the higher the speed of sound propagation.
so granite is just a perfect match for sound.
And this is important.
This is the synthetic aperture radar, so it transmits signals, the so-called chirp signals, made this way to resolve the range dimension, while in the azimuth, you see, or rather here,
We have the Doppler effect. So,
it has happened to all of us that we find ourselves facing a car coming towards us while driving. Maybe it honks. When the car is nearby, is approaching, the horn compared to its Doppler zero, therefore to the frequency for which the horn was designed, has a higher frequency. Then as soon as it passes beside us, we hear its original sound frequency, and then when it goes behind, the frequency lowers. So this physical phenomenon helps to solve the other dimension of the image. All right, and here, let's say, for me it was important to try to explain this thing in simple words. See here this diagram. Here we have a satellite radar. This is the drawing of TerraSAR X, and it is a German radar, very good. You see, it flies along the orbit, and let's assume it has to take a photo, capture a photo of these three houses. What we receive, you see, are these echoes. These are the radar echoes. Do you see? These are the data we receive. And these are the only ones. It's not like we immediately see the images of the houses, eh? They need to be processed. Why? Because this image you see is like that photograph I told you about, taken without the lens. Because here we still need to perform the Fourier transform. And how do you perform the Fourier transform? You see, it is done like this. You take the transmitted reference signal, the so-called sharp signal. The convolution integral is done with, let's call it the distant part of these large droplets that are here. See? And we are doing what is called range compression. So we are trying to resolve the first part of the image. You see? Then we compressed the first part of the image. Then, by taking the reference signal, that is the Doppler frequencies that we have received, we obtain the three objects. So we moved from a wave situation after a Fourier transform process to having the particle. The particles are well defined, localized in space-time, because the localization is always done at zero Doppler.
This is an important parameter.
Okay. See, this is another example of focusing. You see, the objects that are displayed not as dots, although particles, they are displayed with a particular function, that is the cardinal sine, which is the sine of x over x, the so-called sync. This makes us understand another very important concept that Professor Malanga has stressed, I don't know for how many years, in trying to explaining precisely the difference between territory and map of the territory. So human beings who are here, always be impossible. Visualize the territory, but what we also see with equipment, in this case with the radar, is always a map of the territory. That is, this means that our map of the territory is this sin x over x function. This since
We will never see a dot, but we will always see a function that approximates the dot.
Okay.
here, we can move forward. This is the part of focusing both in range and azimuth to obtain the satellite image. And then finally, ladies and gentlemen, to the function, to our function. Bidimensional scene of x over x, where we have the resolution values in the range and the resolution values in azimuth. We have finally obtained a satellite image. Well, I'll show you some applications of synthetic aperture radar. For example, it is necessary to mention what is currently state of the art. What is the use of employing synthetic aperture radar for synthetic? We use it extensively, for example, to carry out control or monitoring of the territory. No, it is very important. Why? Because the synthetic aperture radar has a very precise high. It has sub-millimetric precision, meaning that if I position the radar in space and look at an object on the ground, if this object moves slightly, very slightly, the radar notices it. The radar is capable of appreciate sub-millimetric movements of the objects that are on the ground. I'll show you this very simple video, very short video that...
we are simulating an interferometer. We have two coherent electromagnetic sources, you see. We are generating coherent electromagnetic energy with a first radar. With the second radar, you see, what do I get? I get an interference pattern.
constructive interfering. That is, we obtain areas in space where the electromagnetic power density is zero, destructive interference, and areas where the power density is very high.
Constructive interference. Okay. What do we need this for? We need this for estimate.
See? When I use two radars, for example, I can estimate the so-called interferometric fringes of the Earth. The interferometric fringes help me to estimate the Earth's topography in the 1980s from the shuttle's SRT mission. This is very important. The topography was made, thus drawing the topography for the first time of the entire Earth using synthetic aperture radars, a so-called interferometer that was mounted on the shuttle. What do we use this for? This, for example, this technique could be useful for us. It could be useful to us. Well, the video isn't starting, but that's okay. I'll describe it to you verbally. to estimate the ruptures of the Earth. The Earth's ruptures are estimated for measuring, for studying earthquakes and the movements of the Earth. Okay, so here we then move more precisely to what we have done on this project. So, on this project I will briefly describe how to transform photonic energy into phononic energy. This is important. So, with the Possassi professor we realized that any photograph, whether taken with cameras or with synthetic aperture radar, the imaging is not perfect, it's always blurry. Always. Why is that? Because everything moves. Perhaps it's not easy to see with a camera, but the radar, as I mentioned earlier, since it has a very high precision, very high, it is able to detect sub-millimetric movements of the Earth. Okay. So what did we do? We came up with a method, the so-called method of the Doppler sub-apertures, where we did not use the entire orbital synthesis to generate an ultra-high resolution image. That was of no use to us. So we tried to see successfully what would happen if we gave up a little ground resolution. For example, I give up half the resolution, I look at things with less detail. It doesn't matter. But, and then synthesizing the images, for example, we'd have bandwidth, we'd have Doppler bandwidth, we'd have orbit, and then performing a scan over time in the orbit. This helped us to demonstrate that it is possible to transform an electromagnetic wave into a phononic signal, because when we perform the intraorbital scan and by applying pixel tracking algorithms, we noticed that this pixel moved in a way that was consistent with the Earth's movement. Everything moves. This movement, that estimation of this movement applied to the pyramids, where we already knew the pyramids were moved, were put into vibration by the wind, primarily by human activities in Cairo. Per second, and also from a very important phenomenon, and that is the photon-phonon interaction that has the matter. In the sense that the synthetic aperture radar transmits electromagnetic pulses to the ground, a part of these electromagnetic pulses returns to the receiver, another part is transformed into phonons, very valued, because we realized they maintained coherence, they maintained the coherence of the transmitted signal. These phonons went underground, so they were quote-unquote reflections therefore returned from what they encountered underground, and we detected them again in terms of evanescent waves on the surface of the Earth. One thing we didn't, we were like this, and it was visible. So, by detecting these Doppler anomalies, understood to be evanescent waves that were visible on the Earth's surface, what did we do? Well, in this case, I always like to say this, that we designed a space turntable where the stylus, that is the record, the vinyl, is the Earth, the turntable stylus is the electromagnetic wave. It's the light. It's the light. The photon-phonon interaction
is the needle. That is what transmits. It is the interface. What transmits, what modifies exactly the information from of one nature into information of another nature. Okay, and then practically our appetite grew as we started. So practically we didn't immediately start looking underground. Let's try to understand what happens. Let's try to understand the scale we're talking about. How much the vibrations we estimated were robust. So here I will show you, for example, the vibrations we estimated on the high voltage cables that we detected from the radar. You see these high voltage cables. Because the high voltage cable, I don't know if you've ever noticed, if you've passed under the high voltage cables, you hear the ripple of this signal of these cables because they are set in motion by the high voltage, which makes them vibrate, and what we hear is the noise. So we captured this noise from the radar, so from the space, okay? And then basically after we did these experiments, we said, Corrado, here we need to try to develop an algorithm to perform the so-called tomographic inversion. What is it? Tomos means slice. If we have had the opportunity to estimate the evanescent vibrations on the Earth's surface, because no, then it was possible to look underground because mathematics says so. So you see, this is a model that we have sized like springs. You see springs, and with these springs, masses were attached. So the springs that vibrate attached to masses by performing the Fourier transform of the phononic signal. I have recreated the lens that allowed us to see underground. Okay, I'll just suggest something from the past that we did with Corrado, but only to reiterate the fact that that I respect very much, that he did us a great favor despite not giving he did us a tremendous favor because he validated our technique since the Scan Pyramid project months after we had already published the presence of the famous corridor, the corridor nicknamed the Corridor of Discord. He supported our theory, so I am very happy, and I thank him because he actually helped validate our technique. Okay. I apologize if I am a bit tedious in presenting the formulas, in perhaps explaining things to you, but unfortunately, we all need to understand them together, so at least we feel more assured. I'll just show you a couple of examples where we applied the synthetic aperture radar technique, phononic version, to observe, for example, large infrastructures that we have in our national territory, like the Gran Sasso Laboratory. So, the Gran Sasso Laboratory is a physics laboratory located about 1,400 meters deep of depth if measured from the peak of Gran Sasso, then from Cono Grande. From the peak of Gran Sasso. And you see, this photograph is the, let's call it tomography that we estimated. It was one of the first tomographies that I always like to show because it is beautiful from my point of view. It is beautiful.
I would say
It borders on Bazinga in this.
Joking aside, we managed to see the INFN, the National Institute of Nuclear Physics, hence the Gran Sasso Laboratory, with sections of the tunnel. Here it is. This is an enlargement. You can see there's the interferometer too. You can see that in the end. That point you see at the end is an interferometer, and from here the interferometer always returns. We are coherent living beings. No? We are coherent. We live within domains of coherence. Our mantra is coherence, so it is resonance. But physicists also have it, rightly so, because the interferometer cannot function in an incoherent situation. So there will always be lasers that generate coherent light and then mixed right into constructive and destructive interferences. Okay, all right. I'm in a hurry because I'll then give the floor to the professor. I'll just present another case study. So this is I'm presenting the Mosul Dam, which is an enormous dam. We wanted to understand if it was possible to look inside the dam. You see, the dam has a large tunnel inside. It has a big tunnel and an important Italian company, Trevi, Italian Pride, it was commissioned by the government of Iraq to carry out, but it still goes on, the consolidation of the dam. Because the dam is gradually falling apart, it is collapsing and needs continuous maintenance. In short, inside the Mosul Dam, there is a tunnel, the so-called service tunnel, and you see this. I present to you the tomography of the Mosul Dam, and you can see the section, and the darker section, this one here, more blue horizontal, is the tomography of the gallery. Thus, the section of the Mosul Dam, where you can see the gallery. But we had noticed that it wasn't just visible, the gallery. And other nice things could be seen. I wanted to show you them. You see how we came to see the area of the turbines. So we managed to take a picture of the turbines of the Mosul Dam. Because the Mosul Dam, besides holding back the water and thus creating the reservoir for water accumulation for AGA, for agricultural uses, also carried out the generation of currently generates electricity by means of hydroelectric energy. Okay. So we took the image of the turbines. Okay. These are other turbines that we have seen. You see, this is just to show you that it is possible to view the area, let's call it technical, which is inside the dam, inside the energy structure of Mosul. Okay, one last case study is that of the San Gottardo tunnel, and so we did, we generated the image of the subsoil of the San Gottardo facility, and as you can see, you see the tunnel that is inserted into the mountain. This is very nice. I like this one. Here it is. This is the tunnel, which is located really many meters deep indeed. Okay. Just to say then, this method has been submitted for a PCT patent, so an international patent currently active in Malta, this patent. Let's see a bit of the future. What does it?
Will you wait? Okay, I'm done. I'll turn it over to the professor. Thank you.